Gracias. Vamos a esperar un momento o ya estamos atrasados.
¿Cómo se tomó?
Demasiado tiempo. Yo sí, Sí, bueno.
Well, next speaker is Luis Gorostiza, who will speak about some stochastic models in hierarchical lattices.
Well, thank you very much for the invitation. This is not a technical talk, and it's more expository, and it was suggested to me to propose some open problems, so that's my objective. But I have to give some minimal background. And this is joint work. Well, the stochastic models are random walks and percolation. And this is joint work with Don Dawson from Ottawa. Okay, ultrametric spaces, they have a distance which satisfies the strong or non-Archimedean triangle inequality, which is this. And one of the main examples is the p-adic numbers. Okay, there's a lot of work by physicists on models in the p-adic numbers. This is a book by a colleague of ours at CINVESTAV. It has a lot of references on physics papers, but this is a serious mathematical book. And the space that the ultrametric space that we work with are the hierarchical groups. We denote this way the distance. And omega with a sequence ni. These are sequences, x1, x2, etc., where the ith element belongs to the cyclic group of order ni, and only finitely many of these are different from 0, and the addition is component-wise mod ni for each I. If all the ni's are the same, we just denote it like omega n. And one could think that this is similar to p-adics in case n is a prime, but it is not, because here the addition is component-wise mod n, and in p-adics the addition is the usual one. Now these spaces have three representations like this. Okay, this is omega n with n equal to 3. So the distance is not a geographical distance. Up here it is the number of levels one has to go down to find the most recent common node. For instance, the distance between x and y here is 3. Now this kind of model appears in many areas of application, in particular population genetics, because, for example, these three are brothers, they have distance 1. These and these are cousins, they have distance 2, and so on. And the advantage of this type of structure is that the same pattern keeps repeating. Here we have a graph with 3 vertices. This is a graph with these 3 vertices, and so on. And this allows the use of renormalization methods in statistical physics. Now, for random walk, pxy will denote the probability that the random walk jumps from x to y. And in percolation, pxy will denote the probability that there is an edge connecting x and y. There are also hierarchical lattices that are not groups. Well, in the previous case, we could have, say, different ni's. Here we have all n are 3, but here we could have, it doesn't point anymore. Okay. Here we have 3, and here we could have 2 at level 2, etc. But there are hierarchical lattices like this, where here we have 2 and here we have 3. Now, these are not groups, and this is much more complicated because one cannot use Fourier methods. Now, stochastic models on these spaces appear in many areas, mostly statistical physics, especially spin glass. The main name associated with this is Parisi. Also dynamics of proteins and many other areas. And the states, in the case of spin glass and dynamics of proteins, the people who have done this, they have modeled what happens in this way. You have an energy landscape, so these are energies, okay? The states of the random walk are the basins, and the probability that the walk jumps from one state to another depends on the height of the highest energy level. And this is modeled by a random walk on a tree like the one we had before. Okay? So the idea is that, for example, for a jump from here to here, the walk has to jump over 2 delta. So in general, you can this is linear growth of the heights. You can have other growths, and also this could be much more difficult if, for example, we had here 2 and here 3, and also there are models where the heights can be random, and that makes things more complicated. Okay, so I'm going to talk about the case of omega n. I think that's more complicated with ni, more with lattices that are not groups, and more if the ni's are random. And what we are interested in is the heat kernel of the random walk in continuous time, in particular transients recurrence. Okay, what is the hierarchical random walk? In this case, with different ni's in general, the walk jumps distance j with probability rj and lands at a point chosen uniformly among all those that are that distance from the previous position. The transition matrix for this kind of random walk is the so-called Parisi matrix. It's a certain type of block matrix. Now, to have an idea of what kind of result one has, this is was done by Flato and Pitt, and before that, for n equal to 2 by Darling and Erdos. If Fn is the sum of the Rn, Rj's from n to infinity, and Mn is the product of the first n minus 1 and i's, then if this sum is infinity, the walk is recurrent. One can find the transition probability in time t from one point to another, and it is obtained this way. This is done by means of Fourier transform. A special example of is the C random walk, where C is a constant between 0 and n. This is the probability of a jump of distance j. This is recurrent if C is less than or equal to 1, transient if C is greater than 1. And the return probability has this asymptotics as t tends to infinity. Here Hn is a function which is periodic in logarithmic scale, so it oscillates more slowly as time goes on. But the main thing is this power, okay? The decay of this probability. Think of the alpha stable Lévy process in dimension d. What we would have here is t to the minus d over alpha, okay? I will come back in a moment. Come back to that in a moment. Now, the first physicists who worked with this kind of thing were Ogelsky and Stein. They worked with n equal 2. They used different methods. They used the spectrum of the Parisi matrix. And if one compares their results to ours, this quantity for us is equal to T over delta, where delta is the height of the smallest barrier, and T is the temperature. Mathematicians don't talk about temperature, so I don't know. It's a mystery to try to figure out what this means. Now, the C random walk that I mentioned mimics a simple random walk in dimension D, and also symmetric alpha stable Lévy process on Rd for dimensions greater than alpha. If one takes C this way, because not only the long time behavior of the transition probability behaves the same for the Euclidean case and the hierarchical case, but also the potential kernels in both cases, if one uses this other ultrametric in this space, they have the same decay. So these random walks can be used to mimic Euclidean processes in dimension D. And one can do this even for non-integer dimension. For example, this has been done by Dyson in connection with the Ising model. This has been also used in the case of self-avoiding random walks in the critical dimension, which is 4. Self-avoiding random walks are strange because they are not stochastic processes. They don't satisfy the Kolmogorov consistency theorem. But the important thing is that one can also use these hierarchical random walks to imitate what happens in Euclidean cases. By the way, another thing one can do with hierarchical random walks is imitate, for example, symmetric alpha stable Lévy processes with alpha greater than 2, which do not exist. Okay? But in the hierarchical case, they do exist. So the models in hierarchical spaces have more possibilities than Euclidean models. Okay, so some of our results have been used in models in population genetics, and here are two recent papers on that if you're interested in that. Problems. I have spoken about PT as t tends to infinity in the case of omega n. What would happen in general with ni's? What would be the transience and recurrence results? And many other problems of the type in this paper. This paper is this one by Dawson, Wackelbigger, and me. Also, what would happen if the ni's are random? If one looks at the Flato-Pitt result, one would have to study convergence of this random series. Everything is random here. That seems difficult. And also the question is if there are new phenomena. Now, percolation. Maybe I'm going too fast. I don't know. Classical percolation in the Euclidean lattice is, of course, a big area, but there are still many unsolved problems. And in the Euclidean case, there's also long-range percolation, and these are the names attached to that kind of percolation. They consider the probability of a connection between x and y of this form, which is asymptotically like this for large distances. The important things here are the constants a and s. In the case of dimension 1, if s is greater than 1 and less than or equal to 2, then there can be percolation. Percolation, I didn't say what it is existence of an infinite connected set. Okay? Well, in dimension 2, if s is between 1 and less than or equal to 2, then there can be percolation if there are nearest neighbor edges. The probability of nearest neighbor edges is increased. But if s is greater than 2, then there cannot be percolation. Now, going back to the hierarchical lattice, we have mean field percolation. Mean field in general means that by taking a limit, one can obtain an exact result. So we say that there is mean field percolation if the origin or its given vertex is linked by a path to a point at hierarchical distance k. We take the lim inf as n goes to infinity and the inf over k, and if this is positive, we say that there is mean field percolation. Now, to study that, we assume certain probabilities of connection between x and y. So if the distance between them is k, we take probabilities of this form with ck some positive constants. The result is the following. We consider a beta case which in 0, 1, which satisfy this sequence of nonlinear equations, okay, with these conditions. This beta k minus 1 comes from what happens at distance k, and it helps to obtain a result for the following distance k. So one takes a sequence of distances. Now, if the c's increase, and we have these conditions for the first two c's, the purpose of these conditions is to guarantee that this happens, okay, so that this has a solution. Then there is mean field percolation if and only if the series converges, e to the minus c case, And then the probability of percolation is the product of the beta case of the solution of these equations. In fact, this series converges if and only if this infinite product is finite, is positive. Sorry. Example, if the CK is of this form, then there is mean field percolation if and only if A is greater than 1. And the proof uses, in an important way, the theory of giant components by Erdős-Rényi. This is where these equations come from. Now, with fixed n, percolation means that a given vertex, for example, the origin belongs to an infinite connected component, which is called the percolation cluster, with positive probability. Now, with fixed n, things are more difficult. We can only obtain sufficient conditions for percolation or non-percolation. In that case, we consider probability of connection between x and y of this form, depending on k and constant ck, a delta and constant ck, if the distance between x and y is k. And there are three cases, two non-critical and a critical case, which is delta equal to 1, which is the transition between non-percolation and percolation. The theorem, if d is greater than 1, and the CKs are bounded, then everything stays within a ball, so there's no percolation. If delta is less than 1 and the inf of the CKs is large enough, then percolation occurs. I won't go into the details of what this means. And the important thing is that the percolation cluster is unique. Now, in the critical case between these two, that is more subtle, so one has to take some more special forms of the CK. So we consider this form, which includes logarithmic and polynomial growth. The most interesting case is the case where the C2 is positive. And in that case, if C2 is sufficiently large, then there exists a unique percolation cluster of positive density, which depends on these three parameters, to which the origin belongs with positive probability. The proof uses many things, ultrametric random graphs. I don't have time to explain what these are. Connectivity results of Erdős-Rényi graphs and renormalization methods of statistical physics. Now, for fixed n, one can compare with long-range percolation on the integers, which we saw before. If we put this ultrametric on omega n, the comparison is by taking S in the, I'll remind you what the previous model was. This one, okay. So I'm talking about that now. So if we put S equal to delta plus 1, the case S between 1 and 2 strictly less than 2 corresponds to delta less than 1. So the results correspond in this case. But in the case delta equal to 1 and S equal to 2, there is no comparison because in our model, we have the CKs that depend on K. This would correspond to the A in the Euclidean model, which is just a constant. So this is another example of how the ultrametric models allow for more types of, say, a larger variety of results. Now, we didn't expect anybody to be interested in these results, and we were surprised to find that there are references to this, in particular this one, connected with infectious diseases. Now, problems. How to relate the mean field result n goes to infinity and fixed n. Also, percolation in omega with different ni's. Also, we prove percolation of positive density, and there's a question, for example, a single path that goes from 0 to infinity, that would be 0 density. And also, one could consider long-range percolation in the Euclidean case, allowing the A's to depend on K. Now, a simple random walks on percolation clusters. If one considers the walks on percolation cluster, one could look at a hierarchical random walk, like I described before, on the cluster, but that is very difficult because since the cluster is a disordered medium, then the walk is not symmetric. So instead of that, what people do is they consider simple random walks that jump with equal probabilities to the finite many neighbors in the cluster. But since the cluster is a disordered medium, the traditional methods using Fourier methods or others cannot be used. So instead of that, people use the electric circuit theory, which was introduced by Doyle and Slale. And there's an excellent book now by Lyons and Perez for probability on trees and networks. Well, I'll skip this. Now, background on SED. Sorry for saying SED, but since this was done in Canada, I'm going to say SED. Background on SED-D. We know, as Bojdecki would say, that every child knows that the walk is recurrent in dimension less than equal to 2 and transient otherwise. Now, it turns out that the same results hold in the case of random walk on the percolation cluster, and this was done by agreement Kesten and Chang using the electric circuit theory. Now, okay, let's go back to the simple random walk on SED. We have seen that it is transient if S is between 1 and 2, and recurrent is if S is equal to 2. This was done by Berger. Now, going back to the ultrametric model, we consider probabilities of connection of this form if delta is less than 1 and the distance is k. And if delta is equal to 1, remember that we had this C2k to the alpha. We consider then this type of probability of connection. Then the result is that for almost realizations of the percolation cluster, so this is a quenched type result. If delta is less than 1, then the walk on the cluster is transient. In the case delta equal to 2, it's more interesting because we can have both recurrence and transience. There is a critical value of this alpha such that the walk on the cluster is recurrent for alpha less than the critical alpha and transient for alpha greater than the critical alpha. So the proof uses the electric circuit theory, thinks about graph diameters, and renormalization methods of statistical physics. Problems. Analogous questions for this type of ultrametric space with different ni's in general. Now, from the proof of this result, we have this critical alpha that divides transience from recurrence, and all we know from the proof is that the value of alpha is in the interval 1 to 6. So a natural question is, what is the exact value of alpha, and also whether the walk at the critical alpha is recurrent or transient. Now these results are in this paper, and this is an expository type paper that contains more open problems. Now, estimates of the heat kernel of the simple random walk on percolation cluster. So going back to this case that I have mentioned already several times on the integers, there are these two papers by Crawford and Sly who have studied this problem of estimates of the heat kernel and scaling limits, and a simplified version of the results. If omega is the realization of the percolation cluster, then with probability 1 there exists constancy 1 and delta, such that for x and y in the cluster, the probability of transition in time t from x to y is bounded by this expression for large t. This is the degree of y. This is a power of logarithm. They say that this should not be there, but they have not been able to prove it. But the important thing is this. So this shows that this is analogous to alpha stable process on R with alpha equal to S minus 1. And they also show, they define Xn to be the simple random walk on the percolation cluster defined this way, similar to Tomsky's theorem. And they prove that for almost realizations of the percolation cluster, this converges in distribution to an alpha stable process with alpha equal to S minus 1. Recall that here S is between 0 and 2, but less than 2. And in the case S greater than 2, we already know that there is no percolation cluster in that case. So what they do is that they add all the nearest neighbor connections. So the percolation cluster in this case is the whole space, but the point is that the random walk can have the nearest neighbor jumps, but also the long range jumps. And in this case, there is convergence to Brownian motion. So the interesting thing here, which people worry about, is that there is a discontinuity of the heat kernel at S equal to 2, because in this case, if we put S equal to 2, we get alpha equal to 1. So there's a jump in the behavior at S equal to 2. Now, our problem, which we would like to look at, maybe, is to obtain analogous results to those of Crawford and Sly for a simple random walk on the percolation cluster of omega n. Now, last topic, degree of transience and spectral dimension. Now, for a random walk on set D, or either set D or omega n, the degree of transience is the supremum of A, such that the expected value of the eighth power of the last exit time from 0 is finite. The notion of degree is more general, but in this particular case where these things are countable, one can give the degree of transience by this expression. On the other hand, there is a spectral dimension for a simple random walk on an infinite graph with n-step transition probability like this. The spectral dimension is defined this way. If one looked at this on the whole space, this would be just the dimension of the space. There's a conjecture by these physicists, Alexander Orbach, that for the random walk on the percolation cluster of set D at the critical probability of percolation. Now, in percolation theory on set D, this is the nearest neighbor percolation, Bernoulli percolation. There's a critical probability which divides non-percolation and percolation. And this, for dimension 2, this was proved by Kesten to be equal to 1/2, and it is not known for any other dimension. He also proved that at the critical value, at the critical probability, there is no percolation, okay? And that has been proved also for dimensions greater or equal to 11. Now, these people, Alexander Orbach, they conjectured that for random walk on the percolation cluster of set D, the value of the spectral dimension is 4/3, and this was proved to be wrong for D less than 6, but it is now known to be true for dimensions greater or equal to 11. This is for nearest neighbor percolation. Now, but this is on the so-called infinite, incipient infinite clusters. This was studied by Kesten. The thing is this, that it is known, at least for some dimensions, that at the critical percolation probability, there's no percolation. So the infinite percolation cluster is obtained by a limit conditioning the percolation cluster to be infinite, okay? Now, there is a relation that Dawson and I obtained between the spectral dimension and the degree gamma, which I introduced before, which is this. So for the spectral dimension, there are recent results for different types of percolation, nearest neighbors, spread out long-range percolation, by these people. And our problem would be to say something about gamma and the spectral dimension for percolation on the hierarchical group. That is something that we'll probably never do, but maybe some people will be interested in doing. And well, I have not mentioned anything about my joint work with Tomasz and Anna, but at least I can show you a picture of us.
Are there any questions or comments? So in this model, so you have a random walks basically random media, right?
Yes.
And so does anyone have been studying the limiting behaviors on this process, on the percolation process or something?
Well, the Crawford and Sly, the ones I mentioned.
Yeah, but
And
some like having some estimates on the log of if they have log of iterated logarithm or.
Well, probably in the case of nearest neighbor percolation on the Euclidean lattice, there's a lot of work. There's somebody in Canada at UBC, I can't remember his name now, who does that kind of thing, and there are several other people.
Omer Angel?
Huh?
Omer Angel? No.
Well, he's one, but there's another.
There's another one.
There's another one.
Any other questions or comments? If it's not the case, let's thank you.
Thank you.